Welcome, everybody. Also from my side, I'm really happy to introduce you into this topic, glass core substrates, and give you some insights of what we at Fraunhofer IZM are doing. We split it up this into two main topics here. I will give a short introduction and talk about the motivation. And Julian will take over with some basics about glass, cutting glass, TGV structuring, and also manufacturing optical waveguides. And then I'll have the honor for the rest of it, let's say, to make it an electrical PCB-like construction. We will talk about constructions, TGV geometry, metalization of them, reliability of them, and get to a summary. Okay, to get you all into the same boat, let me start a little bit with first some definitions. Glass core substrates, what are we talking about? They could look like that, but we know from academia there are a lot of variances that you could do with glass cores. We just want to point out at first, this will be like the focus of our talk. Of course, you can etch cavities into glass, you can have way more functions into glass, and they could look in other and really specific ways. But this especially right now has to do with the first product that are coming up. And this is also the reason why we talk about this. So it has a symmetry axis in the middle of it. That is always good if you have RDL from one side and it's not necessarily a low stress RDL. It's always good to have a symmetry. And glass core substrates, they are being targeted on a larger scale. And these are not really some small pieces that you want to create. So symmetry will always help you against the warpage. And one side will be facing towards IC and die, and the other tend to face more towards PCB or motherboard. But there are also some construction where they will replace the motherboard and they will itself act like that. How can you use this? So today, different products are being right in the target for glass cores, like ultra-thin mobile device substrates, interposers with optical interconnect, some LIDAR substrates, of course, photonic MEMS, because you could use the glass for photonic, RF components, some main about interposers for HPC, and you can also have cavity embedded devices where you have lots of more, not only passive glass core, but also active ones. How can you use such a strategy and where? We will focus on 2.5D, 3D interposers for HPC. And just to give you also a perspective that you might all have already seen, as I expect you also to be some experts in your way, and being interested in this talk requires also to have some knowledge about that. So YOL is in everybody's mind. And I found it really interesting what they have shown here. And the basic idea is there are some struggles with the embedded bridge. And also cost-wise, it is maybe good to replace this interposer. And both of these could be solved with one clap by using glass core substrates. And this makes it a really interesting R&D field. And this is what it's all about. Now Julian will take over and give a talk about the basics.
Welcome from my side. Let's start with the material glass. Why glass as a substrate material? A few years ago, we were often asked this question, and in the last year, it's become less. And nevertheless, I would like to briefly discuss this topic. Glass has excellent electrical properties that you can take for DC and HF applications, and you can make electrical waveguides directly on the top of the surface. Glass has also good optical qualities, like the optical transparency over wide wavelengths, and it's a wider wavelengths than most other materials, but I will focus on this later, this talk. We have a good biocompatibility, and that's especially interesting for sensing application. And then we have the possibility to make really small TGVs. So copper-based TGVs in glass that will be also a big topic of this talk. Another strong advantage of glass is the high stability in dimension, and especially in comparison to organic substrates. This is really important for high density RDL, like 2 micrometer line space. The next advantage of glass are the low costs, and it's often named as a disadvantage, and if it's compared to organic substrates, but compared to silicon or other substrates with these optical qualities, for example, it's really cheap. And I'm sure that it will become cheaper when the market for this will grow. The chemical resistance is another important point. It's an important point for the product itself, but it's also important for the process chain. So we need this to get the glass through all of these manufacturing steps. Another advantage of glass is the hermeticity. We use this, for example, to create micro vacuum chambers for cold atoms and so. So it's really important if you want to laser weld the glass and if you want to build up on top of the glass. But there's also a challenge with glass, and this is the fragility of glass. So to be positive, there's a steady development to lower fragility, but it's still the highest challenge if you want to have the glass through the whole process chain without breaking. But you have to keep in mind that 20 years ago, nobody would have thought that it was a good idea to use glass in a cell phone. And today, the front and the back of a smartphone can be made of glass. And that's the most important about this is that the glass edges itself have the main influence on the robustness. So cracks nearly always start at the edges. And you have a more robust glass if you have a better edge quality. And that's really important to know. And that's why we are focusing on the glass cutting and of the cutting of the glass. So we are using a CO2 laser, or in future, we will also use a blade to cut the glass, to have good quality edges, and to have also optical quality of the edges to connect optical fibers. Another important thing is the chemical strengthening that we can also do at Fraunhofer IZM. We have an ion exchange in a molten salt bath, and we have an ion exchange with a dip coating process. This is a really new process. And with both of them, we can make the healing of the micro cracks by compressive stress. So we can have an ion exchange, replacing sodium ions at the surface with potassium ions. And then the glass, especially the edges, are more robust. But the challenge is not solved now because the glass edges inside TGVs, and you can have a lot of TGVs in a glass core substrate, have also a strong influence on the robustness. So as an example, if you have 1 million TGVs with 50 micrometer of diameter, then you have 157 meter additional glass edge. So it's the same story. If the cracks always start at the edges, then a more robust glass core substrate is a glass with better edge quality TGV holds. And that's why we are using a 3D SLA system to investigate various hole geometries, and this all with really high edge quality. And we are using a 3D system to have a focused laser that modifies the glass. And after the modification, the modified areas show a much higher etching rate in KOH. So we can etch this. And after this, we have the structured glass. And the advantages are that we have a 3D process. So as you can see here, we can make hourglass shapes for the TGVs, and this can be important if you want to fill them afterwards with copper. And but we also can have really great TGVs, and this can be important for high frequency application. With this 3D process, we can have various glass types, and we can process glass thickness up to 5 millimeters. The main disadvantage here for this process is that the process is really slow. So we have 1 second per hole. And if you remember the 1 million holes there, 1 million seconds is a long time. And at the moment, the process is not available for panel level, but we are working on this and we are planning to scale this up. Another important topic, and that will be relevant in future, are photonic glass core substrates. And one important property for photonic glass core substrates is the optical transparency of the glass, especially at the telecommunication wavelengths you can see here. And we are using this to create waveguides into this glass. And there are 2 methods available at IZM to integrate these waveguides. We have the femtosecond laser writing. So this is a direct writing process of waveguides, and it's flexible in 3D. So you can write waveguides in different layers. And we have the ion exchange. And this is a process that's based on lithography. And then it's a multi-batch process because you can make multiple glass into a molten salt. And then there, with this ion exchange, the waveguides are created. And this process is much more robust. And that's why on the next slides, I want to focus on the ion exchange. So the process for this is really equal to a process that you all may know from your smartphone displays. It's a chemical strengthening. So we have the molten salt, and in this molten salt, there are potassium ions, and you can make an ion exchange with the sodium, and then you can induce stress into your glass. And if you take silver ions instead of potassium, you also increase the stress inside of the glass surface, but you also increase the refractive index. And this is the way we are doing our waveguides. So if you take a metallic mask and you make this ion exchange just there where you want to have the waveguides, you can locally increase the refractive index. And in a reverse ion exchange, you can take the silver ions that are directly on the surface of the glass, and you can exchange them with sodium. And afterwards, you have a buried waveguide. And these waveguides have really excellent properties. So we can make them single mode and multi-mode, depending on the parameters for ion exchange. They have really low propagation loss of 0.06 dB per centimeter at our telecommunication wavelengths, but they're also transparent for visible light. And we can make them into glass up to a size of 1440 by 305. And we are upscaling this process in the moment to the large 515 by 515 panel size. And these glass can be integrated into a standard circuit board, and the mode field of the waveguides can be adjusted to optical fibers to have their really low losses. So we have the optical part with our waveguides, and we have the glass, the structuring of the glass and the cutting of the glass. And Ruben will now take over to go deeper into the metalization.
All right, now let's dive into some of the points that make glass an electronic substrate. I really like to give a short overview and examples of 2.5 and 3D R&D history. As Erik has already introduced, there has been a long history of R&D into different kind of substrates, and organic substrates were leading it quite a way. But oldest thing I found, and I bet there is even older ones, was HUT from Loughborough University in 2006. And if you look already into it, you can see clearly the same elements as everybody is chasing today. Like we have these optical waveguides from the VCSEL to the detector already. We have glass sheets laminated on top of each other. Of course, it doesn't look like the same things that we are doing today. And we really have to say it was an enormous pre-thinking of what could come up. With this being catching up, our colleague Michael Topper also in 2010, yeah, he found that this could be hermetically sealed sensor concepts, and you can already see some of the elements that we today often draw in these glass core substrate stuff. We already see a glass interposer. This was made on wafer, and then with some further thinking from Sukumaran, Georgia Tech in 2010, we can already see that this is really, really close to what we are today doing. And this is like 14, 15 years old. So we can conclude there had been different waves of interest and different waves of technological advancements in all of that field. It was quite interesting, at least for me, looking into it, that already in 2011, Lin from TSMC, they have an extensive simulation and also built up PCB in comparison to glass. And they have already found some really interesting things, so it's worthwhile to look into it. Meanwhile, Tumala and all of the Georgia Institute, they are really strong into this glass core. They have shown you could do this on both sides in 2007 already. And Kim then had also pre-thought about using all of this in an interposer with stacked memory, HBM, silicon dies. This is everything that you need for the so-called chiplet waves that you have today. And of course, then you can do much more with the glass. You can embed some ICs into it or some active components. Or as our colleague Krönert has shown in 2020, you can further extend all the functionalities by using glass in half-edged cavities and doing hermetically sealed sensors. While overlooking these architectures, we see they all needed to have, let's say, things in common. They needed to have metallized TGVs. And let's dive into it. How did this technology evolve over time? We clearly see that it started with even abrasive mechanical or laser abrasive processes where you just try to use shear force to get a TGV. These were quite large. They were far beyond from straight walls. They were really more V-shaped, and it often more looked like an accident than doing it with precision. We've seen copper was plated directly on glass. It was done conformal. We were far away from filling it, for example. And we simply use dielectric that you need for the RDL to fill these holes. Next step was done by doing it in a way that you at least close one side of the TGV. So you can lower the TGV diameter. That was done in the same time. All of these SLE processes came up. And this was one of the brilliant moves in R&D and academic world that we found, not we as Fraunhofer, I mean we the academic world, we found that you can modify glass with a laser, and then you can etch it. And this was really a great breakthrough. So from one point to another, you can create really, really great TGVs. More of these technological enhancements came when it was able to fill it with a dielectric, to close the TGV from both sides, so they are more compatible to the RDL processes, typically being done with spin-coated resists. But also going into large panels, we see films, for example. But it's always good to have a closed one, to have not an air gap in between. But this is only from the processing side. It is always important to also look on the TCT tests and the reliability of this. But this could be better. Now, the next phase was to find out that you need a buffer layer somewhere in between copper that has really higher CTE and more extreme differences of what the A modulus is. Now, the thermal stress is a product of CTE and A modulus, and of course this couldn't go on. So at a certain dimension and at a certain degree of copper volume to glass, for example, these things will simply break. Buffer layer helps a lot. And then, as been said, if you go down with the TGV even further, then you can use a copper fill. You can have copper on glass again, and this could still be reliable. Now, let's step a little bit back from the schematics and have a look on real TGVs with perspective to the timeline. So on the left side, these were the, say, first generations. We have Sridharan from Georgia Institute 2010. Of course, they were also working on this, but as this is an IZM talk, we want to also show some experiments and results from us. Markus Wörmann was really working on these one-sided closed TGVs already on aspect ratio 1:10, and Grünert in 2022 even achieved 1:12 already. But these are technology enhancements to fill it, to make it electrical conductive. But looking into what could be possible with glass, we can just ask some of our partners like Schwietering, and they can already create 1:15, 1:20, and even further. Now here, extensive R&D is being required. We need to fill this with copper to make this a connection from the top to the bottom side. And this is a major point to solve in the future. Now, let's look on the reliability of all of that. What have we learned over all the time? So right in 2014 and 2016, and it has already been said that, of course, the copper via thickness is a problem, and the via diameter will then also increase this. So it all points to the connection of copper and glass is per se not the best combination. So you need some kind of intermediate partner that really makes a handshake between both of these materials. Well, copper is a really good conductor. We want to stay with copper, and glass is so beautiful from its X, Y, and Z dimensional stability, and providing so many pros that we need to find a way to solve this. For example, it's important with copper after plating, you will need to have an annealing. Of course, it's important to not do this too fast. This has been shown from Okoro and Corning Research in 2020. And similar to this is thermal shock cycles from Wang in 2024. This is quite new. Both of these indicate in the same direction. Copper is creeping at some point, and copper could do some crazy stuff. It is not only elastic, it will go also get into plastic deformation. And you should better not allow copper to do this, because then you're creating some really awful defects. But this has been learned, and we can come along with this. If you don't do, or if we don't do, we typically create these cracks directly at the TGV or surface cracks, because copper is bonding so well to the glass that if you don't have a buffer layer and some intermediate stuff in between to handshake these both materials, the copper will simply shear out some of the glass. And to conclude it, Fujimoto from DNP in 25, they have shown all variants working fine. They have full filled, conformal filled, one-side filled, and all of them are working really great when it comes to RF impedance and input-output matching, and also some really high TCT values. But these results right now have to get into more RDL layers and into real products. Let's conclude this a little bit. Glass core substrates, they are an upcoming but not yet mature technology. We have lots of experience with advanced organics and silicon, and glass core is like the next thing around the corner. Experimenting with this material, we can quickly see that doing RDL on GCS is really a game changer. Also with TGVs getting into 50, 40, 30, and even below of it, these are some connections that you could barely create in advanced organics. No chance. Also the RDL, it is like a quick play. But as indicated below, there are a lot of question marks, like how to solve thermal performance, how to handle all these substrates, because glass is brittle, as we all know. And what about the cost, how to drive them down? What is really the reliability of the package in the end? And now we could conclude with, okay, somebody is going to solve it in the future, but there's one more thing to say here. And this is about our glass panel technology group that we are building up. This will be a group of partnering companies along the GTS process chain, and we will put into our integrated panel RDL line. We can do panel sizes up to larger scale. We can do design, reliability. We will analyze this and do a transparent cooperation with our members that are joining this group. This could be material, process or process control, or even customer voices. And three main goals will be driven here. The first one are overarching factors, where we will discuss roadmaps, specifications. We will form a company network, and also we want to do some standardization work. And the second one is we want to further explore glass core substrate building blocks, like how do we create the panel? How exactly, what would be the best known methods for the TGV process and metalizing it, and then doing RDL on it, and how to control all of that within the process. And the third important main project goal is the generation of reliability data. We will start in parallel with an advanced organic core substrate, and we will compare this to an identical glass core substrate, and then go on over the next years with more sophisticated designs to show where really the barrier will be reached, the technological barrier from advanced organic substrates, and where glass substrates can take over. This being said, I can also thank you for visiting this. And I think Julian and we are ready for your questions. Thank you.